WebRTC was developed for real-time video conferencing using browser-to-browser connections. Today, I'll introduce you to three of the most common WebRTC architectures. Mesh, where all of the clients are directly connected via web browsers. MCU, or multi-point control unit, where a central server processes all video streams and sends back a combined video stream. And SFU, selective forwarding unit, which receives all video streams and forwards them to clients as needed. Mesh is one of the most common architectures for multi-party video calls. In a full mesh network, each participant establishes a two-way connection with every other peer on the call. No server is needed for this architecture, making it a relatively inexpensive option. The downside to using full mesh is that as the number of participants increase, CPU and network bandwidth increases. Network bandwidth is usually the limiting factor in a full mesh network. In a mesh network, every client has a direct connection. In this example, with 4 clients, each client will need to manage 6 connections, or 3 two-way connections. You can see how this can get messy fairly quickly. Mesh was one of the initial implementations of WebRTC. Used for video conferencing between small groups, a peer-in is one example of WebRTC video conferencing in an app. In this architecture, each user will need to send its media to all other users in the session, as well as receive all the media from each of those streams. Most video conferencing apps that use the mesh architecture are limited to only 12 concurrent video users. In an MCU architecture, a central server does the heavy lifting, reducing the burden on the clients. An MCU requires a high CPU or compute power and also high bandwidth to process user requests in real time and forward the streams to each user. An MCU server receives the video stream from each participant, tiles the decoded frames with the streams from all participants, and then encodes the tiled video to send back to each participant. Using an MCU architecture will greatly reduce the number of connections and compute resources needed for each client. However, it introduces a single point of failure with an MCU server going down. This example shows an MCU architecture with 4 participants requiring 2 connections each. BlueJeans is an example of a WebRTC application that uses an MCU architecture. All users connect to a central BlueJeans server, which tiles the video and sends back a combined feed. BlueJeans also uses data channels to add collaborative features like whiteboard and annotation. Most video conferencing apps that use the MCU architecture are limited to only 25 concurrent video users. One common way to scale real-time streaming is to use selective forwarding units, or SFU. An SFU will receive the broadcast in real time and forward the broadcast to subscribers. As the name implies, the selective forwarding unit will receive all media streams and have some intelligence to determine what streams to forward. The additional latency of the SFU is minimal because it will not buffer any incoming video, only forward the video according to its rule set. Using selective forwarding unit will reduce the total number of connections needed for each peer. Participants can request the stream they want to view at a bit rate that is appropriate for their internet connection. Participants with a slower connection will be served a stream with a lower resolution or bit rate. Peers do not have direct connections to each other, only to the SFU. Google Hangouts is an example of an application that uses the SFU architecture. The layout is referred to as Magic Square, where the loudest speaker becomes the largest image. A selective forwarding unit doesn't process video, but rather routes it to everyone who needs it. Each browser sends its media to the SFU, which then forwards that media to all other participants. Most video conferencing applications that use the SFU architecture are limited to 25 concurrent video users.